Welcome to the users meeting, the last day, which is now the micro symposia. And our micro symposia is called Operando Science of Functional Energy Conversion, Storage, Materials and Devices. So why is that? Why we decided to organize a symposia around this topic? Because as you heard from understand the materials, how they behave in their native environment. And it's structured the symposium that we're gonna have some electrocatalysis talks in the morning, then we move into the CO sequestration and CO2 conversion, and then the afternoon will be devoted to the batteries. I would like to stress one thing, and that's this topic is really important because we need to decarbonize the energy sector and the society. And of course, for this, we need to develop all sorts of technologies. So what this symposium aims to really merge, you know, the fundamental science, fundamental understanding about the materials to the actual understanding of the materials working in the device. And that's really big task. And we'll see how far we're gonna get and how we use the X-ray source. So let me now please say thanks to the organizing committee. It's Karsten, Alberto, myself, Marta, Rafael, and Quentin. And of course, Claudine, she's not here. She was organizing more from the organization side. Then there's like few organizational stuff, right? So we have to take a photo at the coffee break, at the end of the coffee break in the mezzanine. Okay, so in the hall, so we're gonna like stand at the bottom and Shanta will take the photo from the top. And of course, there needs to be beer in the evening so we can celebrate the successful day. So O'Callaghan, the typical suspect at 7 p.m. So that's it. And I will, let's start with the first talk.
Hello, everyone. First, thank you as well on the name of the organizing committee for making this UDM3 the most attended UDM. So thanks to you, we are in this nice auditorium. And so I'm very pleased. I'm Raphaël Chateau from CNRS in Montpellier. And it's my pleasure to introduce you our first speaker, our keynote speaker, Professor Matthias Ahrens from the University of Bern. We received a PhD in the University of Bonn, Germany, and then moved to some postdoctoral position, first at the Lawrence Berkeley National Laboratory in the US, then at the University of Munich, University of Copenhagen in Denmark, and now he's a professor in physical chemistry at the University of Bern. And his main topics of research are the nano-electrochemistry, covering applications from low temperature to high temperature fuel cell, and with some dedicated focus on the catalyst degradation phenomena, as you will see on this talk today, I guess, and also interested in the selectivity of our synthesis of valuable chemicals. So thank you very much, Matthias, for accepting our invitation.
Yes, thanks a lot for the invitation. It's really a pleasure to be here. It's actually my first user meeting. So before I start, I would like to introduce the people that did the work I'm going to present. So it's Johanna, Rebecca, Gia, and Jonathan. And of course, I would like to acknowledge our collaborators at ID 31, Jakub, Isaac, and Raphael. And so I tried to give you an overview of degradation phenomena and how we study them. Okay. So we see ourselves as basic research. So we like to address fundamental questions in energy conversion. So we are interested in conversion devices like fuel cells or electrolysis cells that you see here, and like to take fundamental problems and approach them from a basic research approach with model catalysts. We also look in catalyst synthesis, and then we concentrate on activity, but even more so on stability investigations. So we try to develop new simplified devices that image a real device in industry, but also simplify the use of these devices. Today I talk about fuel cell catalysts. For those that are not familiar, a fuel cell is a device that converts oxygen as a cathode to water. And for this, you need to oxidize at the anode hydrogen gas into protons and can travel through the electrolyte, which in a fuel cell is a membrane electrolyte, to recombine with the oxygen to produce the water. So basically, you have two reactions in a fuel cell, two catalysts, but only one side of the fuel cell is of importance in research, because at the oxygen side, it's where you lose your energy in the conversion process. So the splitting of the hydrogen is very efficient and very low losses. But at the oxygen side, you need a lot of catalysts, and you need precious metal catalysts in order to facilitate these reactions. And even the best catalysts have a huge over potential, how we call it. So a part of the energy is lost into heat. And the catalyst you use look like this. You have an active phase that are metal nanoparticles. These are the darker dots here. And they are relatively small in the range of a few nanometers. And mainly it's platinum and platinum alloys in applications. And you need to make these particles small in order to have a large surface area where the reaction can happen. And in order to guarantee that the surface area is maintained, you put these particles on a support, which needs to be electron conducting. And in applications, that's basically carbon powder that you see here. So you have a high surface area carbon with surface areas varying between a few hundred and up to 1,000 square meter per gram, onto which you support these small particles. And of course, this is a 2D image of a 3D catalyst. So that's also always important. And one important property, of course, is how much active area you have on your particles. If you look at fuel cells, you now actually have fuel cells in cars, for example. And one important topic, of course, is the stability of the catalyst under operation. And Toyota introduced the Mirai 1 and now also the Mirai 2. And there are standardized tests to check how stable the catalyst is. But these accelerated stress tests, how we call them, need to predict lifetimes that are quite long, so at least 10 years. And now that we have very good batteries, actually fuel cells are more sort of to larger vehicles like cars or trucks, where they have advantages over batteries. And these devices, of course, need even longer lifetimes. And it's really difficult how to predict lifetimes on a short test. So we like to do a test a few days or a few hours, and then predict based on this the stability of different catalysts. And that's an almost impossible task to do. So when we started this field, we introduced a microscopy methods, how to investigate degradation phenomena where you could actually track the individual particles and how they react to such a stress test. So based on this, we try to distinguish different mechanisms you can imagine in a catalyst degradation process, like particle migration and coalescence that you might see here, that particles move on the support and then form a larger new particle. But you also have Oswald ripening in electrochemical system. You imagine that you form ions that then redeposit on larger particles. You have metal dissolution, of course, and also something like particle detachment, like here that individual particles fall off the support due to, for example, carbon oxidation. Then we, or the field, try to have stress tests that are more unified. And in Japan, they introduce a procedure how to test these catalysts. One test is a load cycle test, so that you simulate the load of a fuel cell cathode, where you go from idle, so no reaction, to a potential, an electrode potential, where you have oxygen reduction, and you just jump back and forth many times between these two potential and see what's happened. And then there's another test that was introduced where you simulate the cell reversal under start-stop conditions, where you can have a very high potential at the electrode. And that is, of course, something that carbon doesn't like, to be exposed to very high potentials. Nowadays, this simulation is less important because no catalyst actually can take this very well. So they found ways to avoid the start-stop. But all these, let's say, measures to avoid these systems, of course, add complexity to the fuel cell system and at cost. So mainly, we focus on this kind of degradation. And if you now look at commercial catalysts, and these are no alloys, so simple platinum nanoparticles on carbon supports, and with a certain ratio of platinum to carbon. And what you see here are different sizes of the nanoparticles. So one with rather small particles, one with an intermediate size, and one where they tempered the catalyst to get a little bit larger particles, so ranging from 2 nanometer to around 5 to 6 nanometer. And these catalysts now you can, in a specific device, where you just look at one electrode reaction, you can expose, so these are the 3 catalysts, to the stress test, where you just jump up and down and have an oxygen flow, so that you have reaction, and look at the electrochemical surface area, so the platinum surface area before the stress test and after the stress test. And what you see is, of course, that the small particles have a larger area at the beginning, whereas the large particles, as expected, have a lower surface area. You measure the surface area electrochemically by absorbing, for example, CO, and then oxidizing, and based on the amount of the oxidation charge, you can calculate the areas. And what you basically see after such a test, that after the stress test, basically the surface area are very similar. So even though you start up with different surface areas, at the end, you end up with almost the same surface area. However, this kind of test doesn't give you any information what happens and why the surface area is lost. And that's, of course, where the X-ray tools come into play. So here are the different tools that you can apply. And important for us is really to look at the process operando or in situ. So typically we stop the electrochemistry while we do the measurement, so it's more in situ, but there's no real difference. We could also run the degradation test, as it takes quite a long time. And so there are different X-ray tools available. You have the powder XRD, the small angle X-ray scattering. We also, in collaboration, look at total scattering and X-ray absorption spectroscopy. Today, I focus on the two powder XRD and small angle X-ray scattering, but we also, for example, on the Swiss-Norwegian beamline, combine these two. And it's really the combination of different methods that is very powerful. So that's really a specialty here at the ESF, and where you can get much more information if you are able to combine two methods in the same measurement. And of course, you get different information, different length scales, from very small atomic length scales to larger length scales. And today, as said, we combined the XRD and the small angle X-ray diffraction, where you look at different morphologies in the particles. Of course, important in this is to have electrochemical cells that allow to do these measurements. And basically, we use two different configuration of cells. So one is the, which I just call the PSI design that was introduced at the PSI, where you come with a beam. Here you have the electrochemical cell also here, and the beam comes from here and crosses, so to say, your catalyst layer, which is here. So it's the beam comes parallel to the surface normal of your catalyst film, and you can do the measurements while the beam is crossing your sample. It's a flow cell, or both are flow cells, and then there's a different design that was introduced here at the ID31, where you have the catalyst sample and the beam comes more or less parallel to the catalyst sample. And that has some advantages. So as I will introduce later, one thing we are always fighting is the background correction of the carbon signal. And here, by changing the angle slightly, you can actually choose where you are in the sample. So you have that contrast, or that you can change the Z in the sample. So either you are in the catalyst layer or a little bit below, and that you can use for the background. So what can we gain from such measurements? So here, what we wanted to investigate, if we can observe Oswald brightening. So basically, the change of the small population of particles at the expense of the larger particles, as we have seen that small particles are unstable. So, and what we did is we just took these two well-defined commercial catalysts and mixed them. They are just powder, so you can mix them. But of course, the particles then are on separate carbon support. So one carbon has only small and one has only large particles. And if you do a small angle X-ray scattering, you can easily distinguish the two populations. So you can analyze the signal and you clearly see two contributions, one of the smaller particles and of the larger particles. Whereas if you try to do that in TM, it's very difficult to image this if you mix the powder. But in the individual TM, of course, you see the small population, the large population, and that's what you also get out in the analysis of the small angle X-ray. scattering. And then you apply such a degradation protocol and collect the data for small angle and wide angle scattering. And so what we find out that you easily can distinguish the two populations, the average size. It's very easy to distinguish in the data, but if you want to look at the relative number of the population, so how many particles are in the small, how many are in the large population, and how that changes over time, it gets really tricky. So what we had to do in order to get this information out, we took the data or the results from the SACs about the average size and used that in the Rietveld refinement, and then we could determine the phase fractions of small particles to large particles. And what we saw is also depending on where you are in your catalyst layer, that the change in size, but also in phase fraction, so ratio between small and large particles depends where you are, if you're close to the electrolyte or close more in the middle of the catalyst. And it was really complex to analyze this. What we then came up with as a conclusion that it's basically that you have a pronounced degradation of the small particles close to the interface. They are particularly vulnerable to degradation. So, that the Ostwald widening mainly occurs between, not between the size population, but on one carbon support. So basically that we couldn't identify any small particles from the one catalyst ending up on the other, at least in our data, that was not in there. And so that most likely it's more an atomic diffusion on the support, but not ions that from the small population end up on the larger particles. And then on a different beam time, we started to change the protocol. So playing around with a protocol that combined different electrochemical treatment. And then with only SACs, you could see that there's at least a difference if you treat the one catalyst alone or if you mix it. So the large particles under this treatment didn't show any size change. So in this treatment, but if you mix them with the small particles, you saw a very small but identifiable size increase in this treatment. And then of course you can look at different protocols that you can come up with to study these systems, and you see that the combination of these protocols is having a very large effect on how these mixed catalysts react to it. And one thing that is also important is that the small population size not necessarily changes. So you can have a large degradation where the average size of the small particles actually stays more or less the same, but still the large particles grow a lot. So it's very important not only to have the information of the average size, but also to have the size distribution and to have a value for the absolute number of particles established in such a system. And then some work here from the IE31, where they looked at the different stages of such a protocol. And it turned out that it's actually these fine details So everyone uses more or less the same protocol, but what you do in between. So for us, it's this establishing the surface area is very important, because that's a value you would like to have also during or in between the measurements. And what they could show is that this actually is not always a good idea. So if you look here, you have a fuel cell, and you started to prepare the measurement, let's say, and then you start your accelerated degradation test and look here in the XRD, the crystallite size, and you see it changes during this degradation protocol, but not that much. So a little change you see, but then once you start to determine your surface area, so with a cyclic voltammogram, we call it, there you cycle the whole potential range and you go to reducing conditions. And that's where actually you see most change in your crystallite size. So this determination of basically what happened during the degradation test with your surface area is actually what degrades the catalyst. And so in this degradation test, basically you oxidize and reduce the particles. Although the electrochemistry shows that you reduce them, some of the atoms might be still oxidized, and that kind of prevents the melting together of the particles. But once you go to low potentials, then they basically start to form a new crystallite site. So these details in the protocol really have a very large influence on the result. And we actually don't really know what is the right way to design a protocol that really can predict lifetimes in the order of 10 years. So that's a huge problem. So we know that this design is critical, but the design is often a little bit arbitrary, although it's more or less standardized. But it's really important to understand what happens during the different stages of such a protocol. And we know that not only extension to high potential where you have the oxidation, but also the reduction potentials are quite harmful to your catalyst. So one, that was kind of what you can do, but there are many pitfalls and difficulties where we need some improvement of the techniques. So basically in the TM, you look at very thin catalyst layer, but in these operando measurements, you need enough material, and you look at really catalyst layers, so 3D layers, as they are also employed in a system. So you have a few micron thick catalyst layer, depending on your ratio of platinum to carbon that you like to study. And in electrochemical systems, this determination of the surface area is really important, because if you have a thick catalyst layer and, for example, come with a beam through the catalyst layer, and you don't have full connection, electrochemical connection to your catalyst layer, then you might see, for example, oxides at potentials that are very reductive. So that's often reported. But the main question is, is that simply because you don't have electrochemical contact to it? And that you only can know if you measure the absolute area of your catalyst and compare it to the value you expect. So, or the other, if you detect oxide, I mean, in open circuit conditions at air, these catalysts are oxidized or reduced, and you have to see the response of the catalyst in order to know that it's actually under the electrochemical environment. That might not always be the case. So what we saw, the system that is very detrimental to the measurement, it's also very important to guarantee that you have full contact of your catalyst layer. Then you really need, you do degradation by jumping up and down in the potential, and the absolute values, if you want to compare different systems, is quite important to really hit the exact potential each time. But the reference electrodes we use are not necessarily the best. A small reference electrode to make sure that they are stable and that you actually hit the potential that you're supposed to hit. So there's something like a IR drop if you have a large current. So in fuel cells, it's important to have a large current density, but if you have a large current and you have some resistance in your cell, that also means that the applied potential and what the potentiostat applies and the one that is actually at the electrode are not the same. So it's important to know this resistance of your cell. And one very important thing in small angle X-ray scattering is the background correction. So you have the beams going through a lot of carbon particles from the support and also from the what we call a gas diffusion layer. And of course, during this test, this carbon changes as well. So if we try to analyze data and just assume, so we do a background measurement of the carbon, the pristine cell, the pristine carbon, and then we try to apply some degradation tests and just take as a reference of the carbon the one that was not involved in the degradation. You see that it's very hard to fit the data to a size distribution. Only if you can measure the carbon background actually during the stress test, you get at least some results that you expect or some change that you expect. So in this PSI design, we started to have a carbon film and to really have measurements at different places of the sample. So that's basically the catalyst sample, and that's only the carbon. And then to scan basically at different points, two at the sample where the catalyst is, and two where there's only carbon, but the carbon also experience the electrochemistry, that you can look at these points as a background that you subtract from the measurement. In the ESF design, basically by changing the incident angle, as said, you can choose if you are in the catalyst layer or back in the carbon layer and do the subtraction by this. So that's more convenient. One thing in both cases is that it's not exactly the same carbon, but that doesn't seem to matter so much. So as long as you can subtract a signal from the degraded carbon. One thing we are fighting a lot with in the data analysis is, as said, the average particle size is a very nice outcome and it's very reliable. But to get size distribution changes with small angle X-ray scattering operando is not that easy. And it's mainly because the scattering changes a lot. If you have smaller particles, they have very little scattering, and it's changing with the volume to the square. So if typical data analysis software like SASView, you assume a size distribution like a log normal distribution. That is typically what you get after synthesis. And then you can have one size or multiple size. You also have to assume a particle shape. And then you basically have a simulated spectrum you compare to your measured, not spectrum, scattering data that you compare to your measured ones. And but for example, adding smaller particles doesn't change your signal so much. So the amount of small particles is not easy to extract. And so basically in the measurement, you always assume the same size distribution, a log normal. But if you have degradation processes, that might change actually. So it's not given that you always have a log normal distribution. So that's a difficulty in the analysis. So average size is very reliable, but the size distribution for the Oswald processes that are important, it's very difficult to extract. What we then went on to do is more Monte Carlo type simulation, where you just don't assume any size distribution. You just add particles, simulate the data, and compare to the measured data. And by this, it's easier to show growing of two populations together. So that's a different system. I don't want to go into detail. So the size difference is larger. You have small particles of platinum and larger particles of gold. And by just simulating different distributions, you were able to really look at the merging of one population into a second population, and where we are more, let's say, confident about the absolute number of sites. So that's a different way to analyze it, where you don't have to assume given size distributions anymore. And I think that's a more accurate system than assuming a given size distribution before. So to sum up, I think the operando possibilities in these electrochemical reactions is very important, and the combination of different methods is what is really making a difference. The cell design is also very important, and this is a very nice design here, where you can also scan at the different depths of the layer. So I think there's a lot of work required in how to analyze SAX data for degradation processes. And often in catalysis, you see the size distribution results, but not so much information how you actually got to these size distribution. And I think that's really important to actually discuss and show this, because at least for us, to have unambitious size distribution of when you don't have a very defined sample, as commercial catalysts are not always very defined, that can be quite challenging. And one last thing, I mean, these are commercial samples, and what we found is that claiming general effects is always difficult. You take the next catalyst and it looks almost the same and it behaves different. For example, the carbon support is different. So it's very, very difficult to have a general view on degradation, because each sample basically behaves different. So one should be really careful in making general statements. With this, I'd like to thank you for your attention and open for questions.
All right, thank you very much, Matthias. Do you have any question?
Yeah, I can repeat the question.
Right. So when you load platinum on carbon, so what's your loading and how low can the loading be to study this with the sun?
Yeah. So basically, you typically have we have a loading of absolute platinum, like 200 microgram per square centimeter, and the ratio in platinum to carbon can be different. So it's typically 30-50% in commercial system, and that's no problem. But so if we make the layers for these measurements, we say, well, we need around 200 microgram platinum per square centimeter. But it's kind of a rough estimate based on size. Might be different, but that's a good value. So you always try to be in a range where you contact the whole layer. So you make it as thick enough to have good signal and all contact the whole layer through. So what I didn't talk about, so you mix actually some proton conductor into the layer as it is also infused, so that you make sure that the whole layer is contacted. But the only way to know is area. So you know your catalyst amount, you measure the area, and you should get always the same value as it's a normalized value.
Thank you.
Actually, very nice talk, Matthias. My question went in similar direction. So if you have only partial contact, would you be able to see it in the X-ray result, or do you have basically to do the experiment that you are sure that you contact everything what you see in the X-ray beam, because otherwise it's difficult to interpret?
Yeah, I mean, one way to know is, of course, the area. That's why you do this cycles. So if if you have a certain loading, you know in the area measurements immediately if all is contacted in the measurement that does the surface determination. But yes, it's not always that easy. So basically, what I would say, when you see a reaction to your electrode potential of the catalyst, then you can be confident that it's contacted. So that's the way to know.
It may be that you see only a part of the particle is responding, but then the integral diffraction signal, you would see a change, but you don't know whether all the particles are contacted.
I think it's a huge problem that is not enough addressed. I mean, so you see in many other processes that that people report oxidized particles under conditions where it's very hard to imagine that they are still oxidized. And the easy explanation is this one. The more complicated is that I don't know. It's a more sexy one, but you really should be careful.
Is there any more questions? Okay, me, I have one actually for you, Matthias. How do you, I mean, considering the design of the successful, or efficient accelerated stress test for the fuel cell application, considering that now there are some systems, you mentioned them, like that can limit the potential of the cathode inbuilt in the fuel cell car, how in academia it's possible to design ASTs that will simulate an operation of this unknown system in the car?
Yeah, that's a difficult question. I mean, how they solve the problem in the car is just that you don't have any or very little exposure to variation. So basically, the battery buffers a lot of the load. And that means, I would say, that means the following, that to develop catalysts that are more susceptible for load changes would really allow a much better operation of fuel cells. But how to design these cells, these tests, that they can extrapolate it to a real use, I think that it's an open question. I mean, this Japanese protocol, it's relatively arbitrary. And I mean, that was proposed, everyone uses, but it's really questionable if that's the best way. And it, as you have shown, it also matters what you do in between the degradation. So I think from a basic science perspective, it's important to study what happened at each of the steps that you do in a protocol, but then to have tests that really can be extrapolated in from such measurements, I'm not sure if it's possible.
Okay, well, thanks. Is there another question? If not, I think we can thank Matthias again. So our next speaker for today, for this morning, is Raffaello Mazzaro from University of Bologna, Italy, who received a PhD in chemistry in University of Bologna in 2016, followed by postdoctoral positions at the University of Bologna, but also in Sweden at the Luleå University of Technology. And then he went back to Bologna in the CNR IMM, and today is at Bologna as the junior assistant professor at the Department of Physics and Astronomy. Thank you for accepting our invitation, and the floor is yours.
Okay. So thank you for the introduction, and good morning, everybody. I'm actually glad to be here to speak about this experiments we performed basically during last year. So they're very recent results. Everything was basically thought and performed last year. I'm going to talk about the development of an operando X-ray absorption spectroscopy setup for the analysis of cobalt iron mixed co-catalyst in a fully operating flow photoelectrochemical cell. Now, as the previous speaker already told you something about water electrolysis and the opposite process, the fuel cell, what we typically employ in a fuel cell, I won't get too much into it, but basically, in our case, we're interested in splitting water into hydrogen and oxygen. This is typically done, can be typically done in a dark electrolysis cell, such as this one, where we have the two semi-reactions that are performed at the anode and the cathode, the hydrogen and oxygen evolution reaction. Now, this is a typical voltammogram you should see in an ideal world where we only deal with thermodynamics, where the current is flowing in our system resulting from the chemical reaction taking place at about the thermodynamic potential for that specific reaction. Now, actually, we have to deal with kinetics, as was previously told you also by the previous speaker, and this is resulting in a shift in the potential needed to induce this reaction. This is an uphill reaction, it's a non-spontaneous reaction, so we need energy. We need to provide an external bias to promote that reaction. So typically, if we have kinetics limitation for the charge transfer process, which we always have, we get much larger potential. So this becomes not really competitive with other technologies to produce hydrogen. Now, one solution to this issue is to replace the electrode, one of the electrodes. Both of the electrodes are different configurations, but in the simplest one, to replace the anode with a photoanode, in particular a semiconductor photoanode that is able to absorb some light. Typically, this is visible light provided by sunlight. So absorb this light, excite an electron hole couple, and use the built-in photopotential to shift this potential to much lower values. So basically, we need much less energy, much less external bias to promote the same reaction. Now, we still have to deal with kinetics. So in order to improve this system and improve this photopotential even more, we can couple this photoanode, this semiconductor, to a co-catalyst that is basically enhancing the charge transfer kinetics in our system. So that's what we've dealt with, and we're dealing with every day. And this is one of the most promising photoanode configuration, where we deposit the tungsten oxide nanostructure, nanoporous structure on a transparent conductive oxide, and then we coat this tungsten oxide layer with bismuth vanadate layer that is basically improving the light harvesting properties in the visible region, as tungsten oxide is not actually absorbing the visible region. And then we can deposit different co-catalysts on the surface of this structure with different deposition methods. I'm not going to get too much into it. So the final photoelectrochemical cell looks something like this, where we're only basically interested in the oxidation reactions, or the oxygen evolution reaction performed by this photoanode upon illumination. Now here we have two very interesting examples of co-catalysts deposited on such a structure. This is a cobalt iron mixed oxide, and this is a cobalt iron Prussian blue structure. So they're same transition metals, but in a different structure. And you can see that the resulting voltammograms, these are shaft voltammograms where we can directly see the photocurrent provided by the semiconductor photoanode are strongly shifted towards much lower potential with the addition of both co-catalysts. And that is actually telling us that the catalysts are quite efficient and they do what we want. The question is now, why do they work? So what are these catalysts doing on this kind of structure? And basically, we have to investigate the charge transfer dynamics in our system to understand what happens to the transition metal centers in the catalyst, to understand how to improve them even more. One thing I want you to notice is that we have a very thin layer of the catalyst on the surface of these photoanodes. So we have basically to deal, if we want to investigate these properties, we have to deal with a very diluted sample. So and also we're dealing with a sample that is very thick. So we have to work in X-ray absorption spectroscopy. We don't have very much sense to work in diffraction, for instance. And we also have to work in fluorescence, as basically we have a very thick sample. Now, this was a preliminary experiment we performed on these photoanodes, in particular the Prussian blue structure, which is the one I'm going to talk from now on mostly. And you can see here that basically we start from a structure. These iron spectra just shifted on the energy scale of cobalt, just for comparison. And you see that we start from a structure for our catalyst, but then we try to see what happens after a photoelectrochemical experiment that was lasting 12 hours. And we see that both iron and cobalt structure is changed quite a lot. So stains and excess spectra are completely different during the photoelectrochemical experiment. Now, the question was, why does that happen, and when does that happen? Does it happen as soon as we put the electrode in contact with the solution? Does it happen once we apply a specific potential? Does it happen when we shine a light onto our photoanode? To do that, to understand that, we needed to switch to operando measurement. So we had first to design our operando setup. So we developed an integrated system in LISA BM8 beamline here at BSRF. So we basically design a setup that is able to be controlled directly from the control room without touching anything in the experimental latch during the experiment by simply interfacing with a microcontroller that is controlling both the potentiostat, the LED driver. So we have bias and illumination controlled by this microcontroller and directly interfaced with the control room workstation. And then also we have the control of the flow system in the flow of the electrolyte in our system, as we'll see later. And we designed a photoelectrochemical cell that was basically liquid in order to work in helium atmosphere. This is, in principle, we should be able to work in vacuum, but we were not brave enough to try. So we stuck to the helium atmosphere. And this is how the photoelectrochemical cell looked like. This was fully 3D printed cell. So to design this cell, we had to face several issues with the specific sample. So as I told you, there are dilute. Okay, it doesn't like it. This is not me anyway. Okay, here. Let's see if it does like yesterday. Okay, so this is, we had to face several issues, and we designed the cell to face those issues with these specific samples, because as I told you, we have thick samples, we cannot work in transmission, but we still need to have light illumination in the sample. So we designed it to be possible from the back of the sample. So we have the line is impinging on the sample from the back. Okay. Okay. I'm not actually touching it, but it's crashing it. PowerPoint is crashing. Okay, let's try again. No. Okay. It doesn't like the slide. Okay. Okay, I just keep it like this, and then I move to the next one and see how it works. And I don't even touch anything. So, okay. I just pointed with my hand. Now, the cell design was thought in order to have an electrolyte layer on the surface of the photoelectrode that is as thin as possible, as we basically need to work in fluorescence. So we need to have to minimize the attenuation from the electrolyte itself, and also we have to have a thin window. So we work with a Kapton window. And the final thing we need to think for the design of this cell was that we need to work in flow conditions. So we need to flow the electrolyte in the electrochemical cell, as basically we are working with an oxygen evolution reaction, which produces a gas on the surface of the electrode. So as soon as we produce a gas, we start having bubbles, and that is changing the attenuation coefficient of the electrolyte during the experiment itself. So basically, we have unreliable absorption data. So to do that, we design everything to be in flow, and we introduce the free electrode system in our photoelectrochemical cell. And you see here that the resulting, maybe try again with the pointer, you see that the resulting fluorescence spectra in dry conditions and the one during the electrolyte flow are pretty much similar, in particular in the case of the elements we're interested in, so iron and cobalt in particular. So we have a drop, obviously, because the electrolyte is absorbing some photons, but the drop is about 40%, so it's not really a large drop, and it's pretty good for this kind of analysis. Let's try again. Full page. Let's see. Crashed into the floor now. Okay, I can go full page. Okay, maybe I can press it then. Okay, so this is basically just to show you how the integration works in the beamline. So this is the beamline workstation, and here you can see that we have the animation not working anymore. So that we can control basically the exact acquisition software. So this is a real-time acquisition. This is the peristaltic pump control, and this is the monitor of both the light illumination and the potential. So we have a control on all and monitor all the features in our step. And another thing that we designed was a pulseless peristaltic pump designed specifically for this experiment, as basically if we have pressure instabilities, this is resulting in a bulging, an intermittent bulging of the Kapton window. That's actually a pretty big issue, because that is changing the thickness of the electrolyte, and as a consequence, is changing the absorption coefficient of the element we're interested in. And this is not what we desired, obviously. So one by one, I'm sorry, but it looks like. So getting to the excess spectra, this is a comparison of the spectra of the same cobalt iron Prussian blue co-catalyst XC2 with the one we got in the operando experiments. Don't mind for now about the potential, but basically you can already see here, just by stacking them, how that is changing a lot from the XC2 to the operando measurement. So we have both the change in the white line and the edge position, and also the pre-edge peaks. So that is pointing out that we have already, just by putting the co-catalyst in contact with the electrolyte, we have a swift variation of the local structure of our electrolyte. And also you can see that we have some much smaller, but some non-negligible variation of the excess spectrum for different potentials. And these are all in dark for now. So we'll see later what light does in this kind of thing. So this is just to turn this. We just try to do some extra analysis on the sample X to be sure that we started actually from the structure we were interested in. So the cobalt iron Prussian blue, that is, we have cobalt and iron sites at the corner and bridged by cyanide ligands. And this is actually fitting pretty well, not perfectly, but pretty well. And then we looked at the excess spectrum operando. And in this case, we couldn't do excess analysis as the signal is pretty noisy. So in this case, we couldn't really get full structure reconstruction, but we compared the Xen spectra with the literature one we found for a similar cobalt base, and I'm always dealing here with cobalt K alpha for now, with a cobalt, similar cobalt phase, a cobalt catalyst, where it was already displayed that for such catalyst upon the electrolyte contact, this is transforming into this cobalt oxycubane structure, either edge or corner sharing. So this is pretty, I mean, most probably the actual structure of our catalyst during the photoelectrochemical experiment. Okay, and okay, no, that's okay. Now we can have a look at what potential does to the catalyst, and here we have a comparison of the Xen spectra of the catalyst at negative potential, where we expect to have some reduction of the catalyst from cobalt 3 to cobalt 2, and the one we have as 0.2 and 1 volt, where no reduction is occurring, or is expected to be occurring. And as a consequence, you see that the spectrum resisted to minus 0.2 is always showing a small shift toward lower energy, and also an increased wide line, which can be assigned to an increased density of states in the cobalt center. So probably due to the reduction itself of the system. And then, okay, and then we try to see what happens when we shine also the light during the experiment. And with first experiment, you see that we saw a quite large difference in the spectra in off and light condition. And the experiment was performed by collecting a whole spectrum in dark, and then collecting a whole spectrum upon light illumination, upon illumination, and that was actually a bit weird, because we didn't see any trend in the sample, and we couldn't understand why that was happening. So we tried to change the acquisition mode. We implemented a new mode in the beamline that was basically triggering the LED source directly during the acquisition of the excess spectra, so that we could collect energy by energy, both the off and on signals, so the dark and light conditions, in order to have an information about the fluorescence intensity and therefore the absorption coefficient at each energy, and then switch to the next energy to collect the whole spectrum. And as you can see, then in this case, we have good and bad news. The good news is that these spectra are exactly the same one to each other. So on and off, you cannot even recognize the on and off spectra. And that means that the measurement is very stable. So we don't have any problem in the stability of the measurement. But on the other hand, we have some issues that are related to the fact that we don't see any effect of the light. So at least in this kind of experimental setup, we don't see anything, except for a very small change in the 0.2 volt sample, in the 0.2 volt spectrum. You see here, this bump here. And actually, this is actually a real signal, and we confirmed it by looking at the sample with a different acquisition method that is called FXREV. Basically, it's the acronym for Fixed Energy X-ray Absorption Voltammogram. So we keep a fixed ray, we chose a fixed energy for the X-ray. So basically, we chose the absorption edge, E0, the maximum derivative for the absorption edge, and then we sweep the potential in our sample, both in dark condition and illuminating the sample. So you see that basically we see these bumps here when they are corresponding to the minimum potential here, so minus 0.2, where we have the reduction of the cobalt 3 to cobalt 2, and that is something we expected. But also we see that upon illumination, so in light condition, in the case of cobalt iron Prussian blue, we see that these peaks are broadening. So we have a larger potential window where we actually are decreasing the oxidation state of cobalt. So that is something that is fully related to the light in our system. And you see that basically you have, this is repeated multiple times, and we see the same signal. And interestingly, the opposite trend was observed for the other catalyst I showed before. So this is a cobalt iron oxide. And in this case, again, we see these bumps. These are much higher in this case. It's also a different catalyst, so maybe so different amount of catalyst. This is a much larger peak. In this case, we also see some degradation in the first step, actually, of the experiment. But you can also see that upon illumination, these peaks are shrinking in this case. So they are basically the potential windows in this case is reduced in light conditions. So we have an opposite trend for the two catalysts. So now to understand something about the how that works, we try to look at the we try to get mechanistic description from by comparing it with the electrochemical data we have, and in particular we looked at the rate constant for the transfer and combination mechanisms, and we can recognize that basically we're working in two different, in our experiments, we're working in two different regimes. One where we have very fast charge transfer at the interface, which means basically as we are looking at the steady state picture of our system, we're not looking at any variation in our catalyst oxidation state, as all the holes transferred to the catalyst are immediately transferred to the solution. So in this case, we are not expecting to see anything, and that is actually what we saw. While in this case, we're working in a range where both transfer and combination rates are much lower. So, oh shit. Okay, sorry, I have to do it now. Just last night. Okay, so basically, just to get to the end, the explanation we had for the different trend we see in different catalysts is that in open circuit conditions, that is about 0.2 volt where we dealt with, so where we shouldn't have any reduction, spontaneous reduction of the cobalt. Upon illumination, we see two different behaviors that are basically related to the chance of recombining these electrons transferred to the cobalt co-catalyst in the case of cobalt iron oxide. So we have that shrinking of the reduction peak, while in the case of Prussian blue, this process is not taking place. The reason actually is unknown, but this process is not taking place. And this is also this was also suggested by a quite old paper on a similar catalyst to be one of the reasons why the catalyst is working as a catalyst, as basically it is increasing the whole lifetime in the semiconductor, since there is no recombination possible in this case. So what's next? There are a lot of things missing. So these were just the results of 2 beam times. So we're gonna get more in the future for sure. And the idea that we have for the future is first to track the photo-induced charge dynamics by operando pump probe XAS, as basically we're stuck for now the steady state measurement. And also we would like to see what happens with the addition of electron hole scavengers in solution. And the last thing is that actually I forgot on purpose to talk about iron. We couldn't work on iron because we had a strong contamination of the substrate coming from the glass substrate. So in order to get some reliable data, we need to change completely the substrate and try to work with different samples. But that's something we're going to do in the future. So thanks for your attention and impression.